Today's lecture is in continuation to the previous one, where we looked at the importance of a very useful technique called pulse laser deposition, and this has been one of the path breaking event in the area of thin film technology, where you can translate most of the studies of bulk materials into thin films, and not only to study in lower dimensions, but also to bring about lot of device applications into perspective. PLD has been a very decisive method, and we have looked at some of the constraints, how sensitive this process can be, and we also tried to understand the dynamics, especially the plume dynamics, how it affects the growth quality of these materials. Today I am going to concentrate on another equally competing thin film deposition technique, which is called pulse electron deposition. The fact that we are replacing the word laser with electron suggests that the source of deposition is going to be different. So instead of using a pulse laser beam, we are going to use a pulse electron beam, and we can see why PED is more important that way, and what are the advantages and disadvantages of PED over PLD. So in this PED deposition, which is fairly a new technique compared to PLD, we will look at how we can make thin film structures, nanostructures, and how this can be used for device applications. So let us start with understanding what PED is. Pulse electron deposition is a process in which 100 nanosecond high power electron beam, which is approximately of the order of 1000 angstrom at 15 kilo electron volt, penetrates of about 1 micron deep into the target, and as a result there is a rapid evaporation of the target material, and this transforms into a plasma. So once it is a plasma, it gets deposited on the desired substrate, which is actually a non-equilibrium extraction of the target material, and therefore because of this nature of transporting the ions and the atoms, you can ensure a fully stoichiometric composition of the plasma, and that way we can make a single crystalline film. There are some issues which act as strength for PED compared to PLD. Therefore it is better we familiarize why PED stands out in many ways compared to the most established PLD technique. In contrast to other techniques such as conventional electron beam evaporation, the main feature of this pulse system is the ability to generate a high power density of 10 power 8 watt per centimeter square at the target surface. So you are actually focusing this highly intense electron beam on the target, and as a result thermodynamic properties of the target material such as melting point and specific heat becomes unimportant, because you are overcoming all these issues by a high energy pulse, and as a result you can evaporate any sort of material that you want. So this is particularly advantageous in the case of complex and multi-component materials, where you have more than 2 or 3 metals. Then you do not know how these materials would respond to a pulse laser or to a pulse electron beam. You would see they behave in a more friendly way with PED technique. As in the case of PLD, PED provides a unique platform for depositing thin films of complex materials, and therefore it is very viable for applications and mass production, and as a result this is one of the scalable and cost effective high volume manufacturing process. We will look at several examples and understand where it has a edge over PLD. If you recap the previous lecture on PLD, you would see that the instrument itself is quite big, because you need to bring the laser plume into the vacuum zone, and as a result several optics is required, and then you also have the big laser system which is going to occupy. So comparatively PED technique is a very amiable process, because even in lesser space you can try to install this system. As you would see here, this is all the dimension of a PED, and what is important in this deposition technique is the pulsed electron source, which is called PEPS source, and this is the core of the PED technique, where the pulse electron beam comes from this. But for that the vacuum chamber and all the energetics are nearly the same like a PLD. So what you do, you avoid the complex problem of maintaining a gas source for laser, and then the cooling systems plus the optics to guide the laser light into the vacuum chamber. All these are avoided by just using a laser electron source. So this is a typical way that you can energize a material by shooting a pulsed electron beam, and the target is now ablated, and it causes this plume, and then this plume travels to the substrate. Although the pulse electron beam looks very fancy and simple, but to take a closer look, these are the elements that are involved. You have a hollow cathode, and this is focused on to the vacuum chamber. This is the vacuum chamber, and this is your PEP source. You have this capillary tube which is usually a ceramic, and then the hollow cathode here, and this is focused on the target. So critically, although it is simple, but the making of the PEP source is a tricky stuff, which is the most important element of a PED chamber. Now to get a quick look at the cost effectiveness between PLD and PED, before you look at the examples of how the PLD and PED grown films look like, you can clearly see they stand out, because it is almost 1/8 of the cost that is required. So if you are looking for a 1 energy source of a PLD, you may have to shell out nearly $400K of US dollars, whereas PED is just 50K. So therefore you can actually get more than 6 PED chambers for installing one PLD chamber. So cost wise it is very effective, and therefore it is very useful for mass production and deposition station. So PED costs just 10% that of PLD. If you quickly want to look at the dynamics where PED is different, when PED is in operation you would see a channel tube which is also flashing or illuminating during the process, and this is nothing but the ceramic tube which is actually guiding the electron beam, and this electron beam actually falls on the target. This is the target, which is of a typical 25 mm disc target. So when the PED strikes, then you can see the plume is coming out. So this is a typical photograph during the operation process. So the control of this plume and what is happening, the composition and the target which is mounted here perpendicular to the plume, all this governs the dynamics of PED process, and either it can make it more novel or more detrimental to the film that is grown. So this is all we are going to understand in the next few slides as to what are the critical parameters that govern this issue. When we talk about the specification of pulse electron beam source, we need to understand the critical advantage is that you have a pulse width of 100 nanoseconds, which is comparably different to the pulse width of your PLD process, and then the pulse energy range that you have is quite tunable. You can go from 0.1 to 0.8 joules, so you can actually vary the strength of your pulse by operating with a different measure of the energy of electron beam. So when you talk about electron beam, you are going to operate from 8 kV to 20 kV. So you can change 8, 10, 12, 14, 16. So with this the pulse energy also will be affected, but the pulse width will remain the same. So you can actually tune this for a variety of substance, including biomaterials to ceramics to metallic materials to insulators. You can play around with the energy of your electron beam and the pulse energy. Therefore you can make a judicious choice to bring the right mixture. So these are some of the specific numbers that govern the PEP source, and you can also see the beam cross section is pretty sharp, which is 10 into 6 into 10 power minus 2 centimeter square. So you can really spot on a very small area, which means even with a 10 mm target you may be able to do a PED deposition. What sort of materials that we can coat using PED as a thin film? The spectrum is quite large now, and you can see starting from a superconductor to a photonic material like zinc oxide, to a photonic material again tin oxide, or to all these insulators, or to polymeric substance, to ferroelectric and magnetic substances or metallic substances. You see a wide range of compounds that can be used. I2O, of course, you know, is the base material for any photonic applications. So if you look at the spectrum of materials that you have, you can actually play around with almost any material that is possible through PED. And what is the control? You can actually go for a deposition rate of 0.1 to 1 angstrom per pulse, which is a very good choice. So if you want a slow growth, you can effect a slow growth process. If you want a rapid deposition, you can do that. At the optimum distance between the target and the plume of say 6 centimeter, you can actually vary the deposition rate considerably. Now the parameters that control the film growth has some numbers in it. So when you are actually having a substrate which is your single crystal here, and you have mounted this substrate perpendicular to the plasma, now the energy of the arriving atoms here, which is in the end of the plume, and the number of arriving atoms, which together these are n into E1, they depend on the plasma energy balance and the electron beam intensity, which is actually given as J in ampere, volt in kilovolt, and time in seconds. So these three parameters govern what sort of energy with which the atoms arrive at the substrate and the number of arriving atoms. So this is all it takes to control. Therefore for every given material you need to make sure that you have a proper energy balance, because the way you try to evaporate zinc oxide will be quite different from the way you evaporate nickel, for example a metallic material. If you want to ablate aluminum oxide, then you need to have a proper energy balance. So depending on the band gap of the target material and the energy balance that you choose, you can optimize the plume or the plasma flux. If you look at the electron beam generation, which is actually coming from a trigger, and you trigger it through a hollow cathode, and it is actually coming to the vacuum chamber, which is your anode, you would see for a 20 kV pulse, for example, if you provide a channel spark discharge, for every pulse you would see the decay will be of this fashion. This is for the voltage, and then you would see the current going through a minimum and then coming down, and in this process you would see the pulse width is actually full width of half maxima ranging to 100 nanoseconds. So you have a very narrow range where this pulse width is, of the order of 100 nanoseconds, and this is the prime importance for the Pd process, where you have a electron pulse which has a very sharp breakdown, and the pulse width is as close as 100 nanometer. So with this pulse it is possible to almost bring about many changes when the electron beam is actually hitting on the target surface. Therefore, when such a high energy pulse is actually hitting the target, now you can look at how the materials get ablated. For example, the electron range, which is actually a factor of V square, electron range, if you plot as a function of the electron beam energy, you can actually keep on varying. As you would see, the operation at higher voltages are not actually favored. So anything beyond 14, although it can be done, it is recommended that we do not strain the instrument by operating at very high voltages. And also you would see that the heavier metals are ablating much better compared to oxygen. So in case of silicon, for example, the electron range is easily achievable up to 1 micron even with 10 kV, whereas for alumina and yttrium, barium, copper, you see substantially they are lower. So if you are going for 14 kV, it is very easy for you to achieve electron range of the order of 2 micron for a optimum kV of 14 kilovolt. The target heating is actually more dependent on the electron range, and if we have a proper calibration for different materials, then it is very easy for us to choose depending on the target to the plume distance. With this electron range, it is possible for us to determine the target heating, because continuously this nanosecond pulse is hitting, and this target heating range is nothing but a beam power over electron range. So if you know the beam power and you know the electron range, it is possible for you to measure what is the target heating rate. So depending on that, if you make a plot, you would see that it is not linearly varying, rather it is actually going through a maxima. So maximum heating can be achieved at 14 kV, which is a very useful information. So instead of struggling more at very high voltages, if you can optimize for this numbers, then it will be more efficient for you to do the ablation. In other words, for this beam power and electron range, if at 14 kV you achieve maximum heating, then we can try to bring down the other parameters like target substrate distances closer, so that we can work at this efficiency. There is an optimal E beam voltage for PED, and that is what we see here. This is another useful guidelines from Neosera group, which gives us some idea why PED may be much more efficient than PLD. For example, if you take a 248 nanometer laser, krypton fluoride laser, and use the PLD, you would see very comfortably we can deposit silicon carbide, titania, strontium titanate, tantalum oxide, and silicon nitride. These are very easily deposited using a PLD instrument, whereas when you look at the band gap of some of these materials like yttria or zirconia or magnesia, silica, alumina, all these are showing a band gap above 5, and if your XMR laser can generate only 5 electron volt, it is impossible for you to ablate with ease this high band gap material. Therefore, this is where PED comes into picture. So with PED you can actually deposit any of the insulating compounds or compounds with very high band gap. So that is one of the reason why PED still stands out as a more prolific deposition technique. With this in mind, at a distance between the target and the substrate of 5 centimeters, you can anticipate typical deposition rates of the order of 1.6 angstrom per pulse if you are going to deposit yttrium barium copper oxide, which is a superconductor. If you go for ceria, you can easily ablate that. Calcium cobaltite, alumina, silica, all these insulating materials you can easily ablate with a very high deposition rate. And you can also see that the photonic materials you can ablate with fair amount of ease, and these are the metallic materials. Although the ablation rate is nearly 10 times lower, yet it is possible for you to ablate the metallic materials also. So, the type of materials that you have and the electron beam energy that you use with a fixed target to plume distance, you can actually achieve this sort of deposition rates. So, one should not think that anything and everything operated with PLD will have the same deposition rate. So, it varies with the system and how it takes up the electron beam. As you would see here, if this is your substrate and this is your gas zone, and this is your plasma which is generated at the interface with the target, you would see at 100 nanosecond this is where the plasma is, and the kinetic energy of your plasma or the ions that are generated is much higher than 1 electron volt. But as the plasma progresses towards the substrate, you would see in 1 microsecond the kinetic energy is falling down, and it is falling down much lower, and then it becomes a thermally activated deposition. So, we should understand how the plume propagates, and therefore depending on the material it is possible for us to fine tune the system. The flux dynamics is almost similar to PLD, as you would see here. In the first 100 nanoseconds when the pictures are taken, this is your target, target location, and the way the plume propagates this way towards the substrate, you can see the plume is actually getting discharged, or it decelerates in gas, so over a period of the decay time. So, at 100 nanosecond is just about to flash, and then as you go down to 700 nanoseconds, you can see how the plasma decelerates in a particular gaseous environment. And you would also see this white region is the region where maximum kinetic energy is there, and it is still sustaining at 700 nanoseconds. So, with every pulse shot, the pulse actually propagates in this fashion from here to here, and then it goes and strikes on the substrate to form the thin film. Now, I will go to some specific examples, show you some thin films, and also draw some conclusions on plume dynamics and stoichiometry, which might help us understand the dynamics of PED process. Some of the examples are taken from the literature. One is from Nistar and co-workers, who have worked on a variety of oxide films, and they have made quite a good amount of calibration. So, I want to touch on few examples from Nistar's group. This is nice image of the visible emission of hydroxyapatite, which is a bone material, and you can actually translate this hydroxyapatite into a thin film form, not necessarily a bulk form, and you can try to look at the strength of these hydroxyapatite films. And if we have a way to deposit as a thin film, then we can try to do it on variety of substrates. So, here is the situation where you have this target is nothing but your hydroxyapatite, and then you have the substrate, you are ablating using electron beam. Look at the progression of the plume, and this is actually a luminescing plume, because all the ions in your hydroxyapatite, usually calcium, phosphorus, all these are actually fluorescing, and once you trigger the pulse at 0 nanosecond, this is how it is, but they spatially grow with time, and that is what you see here. Over a period of 3500 nanoseconds, it has actually spatially grown, and you can see the zone, the temperature zone, and how the species are still luminescing over this transient period. And during this period, we also understand that the heavier particles and the lighter particles, they take their share to reach the substrate surface, and as a result we can have a knowledge of how complex materials can be grown. The mapping of these flashes gives us idea about the stoichiometry and how the plume dynamics can control the end stoichiometry of the film. This figure gives us the velocity distribution of the species corresponding to the image taken from the previous example of hydroxyapatite. As you would see here, the velocity distribution ranges from 0 to 3 centimeter, which means you have both the high energy particles as well as low energy particles traveling together, and the spectrum is quite large, and this is the one which really makes the difference between Pld and Pd. In Pld, typically you would see the spectrum coming like this, which means you do not have edge for for heavier species to travel, and because you have the velocity distribution of the species quite large, it makes it more versatile for you to prepare films with less particulates. Otherwise you will end up with the thin film with a lot of particle chunks also coming into picture. Because of this velocity distribution, you get a much finer film compared to Pld, and I will show you some example of how it can go through. In this example you will see zinc oxide, for example, if you operate with the discharge voltage of 16 kV and external capacitor of say 26 nanofarads, then what you see here is stoichiometric film, but many particulates are there, a lot of small solids are seen on the SEM surface. But if you are going to change the discharge voltage and external capacitor, you would see for 1426 combination stoichiometric film is there, and it is smooth and very low number of particulates are there. And you can also see the same combination works out for calcium phosphate, zirconium tin titanate, barium strontium titanate. In all these cases, with a proper combination of your discharge voltage and capacitor, external capacitor, you can actually have a very smooth film coming out. This cartoon tells us what is the gamble with the stoichiometry. So in such conditions, what is the stoichiometry of the final film? For example, in this case, this is a RBS, Rutherford backscattering spectra of your calcium phosphate, which will actually estimate how much of calcium is there, how much of phosphorus is there, and how much of oxygen is there. So you can technically evaluate your final composition based on the RBS channeling studies. That is the advantage. And as you would see, the solid line here is nothing but your theoretical prediction, and your dotted line is nothing but your experimental plot. In the case of PED film, you would see that there is a very good match, and both in the high energy region as well as in the low energy region. But notably, you would see for a Pld film there is a problem of mismatch for phosphorus, even for calcium here, and also there is a tailing in the low energy spectrum, that is for oxygen. What does it mean? Compared to Pld, Ped seems to give a very good film stoichiometrically, and that you can see from the SEM micrograph also. These are the small particulates that I was mentioning in the previous slide. So this sort of small particulates are there, but very minimum compared to Pld process, and therefore for complex materials PED seems to be doing a better role. And similarly, if you look at zirconium tin titanate ZST, the RB spectrum is given for both PED deposited and Pld deposited film. As you can see here, in this case there is some problem with the oxygen stoichiometry here, but titanium and zirconium seems to be doing pretty well. And if you look at the PED, oxygen stoichiometry is actually guaranteed. There is no problem here. As a result, if you look at the SEM micrograph of the PED deposited film here and the SEM micrograph of the Pld deposited film, you can see how the grain structure differs. In other words, this surface seems to be relatively much more finer and smoother than the discontinuous grain growth in the Pld structure. Therefore, there are a lot of advantages when we specially play around with complex materials. Pld, because of the energetics that is involved, it seems to have an edge over the Pld process. In the case of PED, the mechanism of interaction with the target is governed by electrons and not by photons, which is the main difference, and thus the energy transfer to the target material is much more effective in a PED process compared to Pld. So, wide band gap or highly reflective materials can be ablated with PED, and this is one of the reason why polymers can also be easily ablated using PED method. In the case of wide band gap materials such as calcium phosphate, it is also shown that the surface morphology of the films grown by Pld strongly depends on the target optical properties. So, any optically sensitive material, they will actually depend on the optical absorption coefficient, say alpha, and if this alpha is not comparable, then the material might throw some plume, but it is not actually ablating. So, you do not have this problem in the case of PED, because it does not depend, the target does not depend on the optical absorption coefficient, just depends on the beam current and as a result beam energy. Therefore, it is very easy to deposit optically active or materials which are optical materials. So, this is one of the reason why Pld is more favored. I would like to give another example of zinc oxide that can be deposited with PED. Deposition of zinc oxide is actually favored in substrates like alumina, because aluminum oxide in this case is actually sapphire, we call it as Al2O3. So, you can deposit zinc oxide on alumina. Reason, the zinc oxide is also HCP and it can easily grow on sapphire, which is also HCP, and if you look at the growth, you would see only the 002 or 004 reflections of zinc oxide, which means it is a C axis oriented growth. So, zinc oxide is actually growing on the C plane of your sapphire substrate, therefore, you would see only reflections of that, and the way you see the intensity of your C axis grown zinc oxide, it clearly shows that they are very highly oriented thin films, and you can make epitaxial films out of it. If you look at the cathodoluminescence, that means you are trying to excite this zinc oxide film using a cathode, then you can see this emission which is very typical of zinc oxide, which approximately comes around 380 nanometers, corresponds to 3.27 electron volt, is clearly seen, and this is a very useful input. You get a very sharp emission, although there is a camelback here which is approximately of the order of 550 nanometer, and this camelback is usually due to the oxygen non-stoichiometry. Nevertheless, the band to band edge emission is very clearly seen using zinc oxide. So, you can make very good highly oriented zinc oxide films using PED. as I told you in the previous slide, this zinc oxide can be easily made with very high degree of orientation. There are factors that we need to bear in mind when we deposit zinc oxide. For example, the beam energy parameter is actually given by this relationship, and it goes as E is equal to C U square by 2, where C is your capacitor and U is your discharge voltage. So, for a capacitor, external capacitor of 26 nanofarads and beam voltage of 16 kV, you would end up with a beam energy of 3.33 joules. So, if this were the case, then you see several particulates are there in this film, and this is not a smooth film, therefore, this is not good for sensing properties. So, what you do, you try to play around with the capacitor numbers and the discharge voltage. Suppose I reduce the discharge voltage from 16 to 14, then E2 will be just 70% of your E1. So, considerably you can bring down the beam energy from 3.3 to roughly around 2.9 joules, and once you do that, you can clearly see the smoothness of the film changes quite a bit. You can see here in B, all the particulates are now vanishing and very few particulates are there. So, what you finally do, you again try to bring down the external capacitor to 16 nanofarads, and for this combination you see almost most of the particulates are avoided in zinc oxide film. Therefore, the beam parameter is very important. You need to play around with this numbers to get the right response. So, the film roughness is very critical to the electron beam energy that you are choosing, and based on this you can see how the profile changes. If you are looking at a polycrystalline film for ZNO, for example, the target to substrate distance plays an important role. If you are going to keep the distance at say 2 centimeter, then you are seeing this 3 peak, which is characteristic of zinc oxide, to be more broader. In other words, it is more amorphous. If you are going to keep it at 3 centimeter distance, then the crystallinity improves and the best samples are made when the critical distance is at 4 centimeter. Therefore, each system has its own sensitivity. We need to optimize that distance. This is a SEM image of zinc oxide that is grown on silicon. You can see how sharp interface you can build using pulse electron deposition. You can either make a polycrystalline zinc oxide film or single crystalline zinc oxide film, depending on the substrate that you are choosing. And this is another example by Venkatesan's group at Maryland, where they made transparent conducting tin oxide films. Why are they used? Because for photonic applications you can now use a transparent anode rather, which can replace indium tin oxide. Because of the cost that is involved, tin oxide films are preferred, and you can see here Pd grown films show nearly 80 to 85% of optical transmission. In other words, it is almost a clean transparent electrode. So, you can get a very good transmission out of a Pd deposited one as comparable to Pld. And here also you look at the mapping of your tin oxide using mass bar. The isomer shift is exactly the same between Ped and Pld. That means you can get a very good oriented film. And here again in B you can see the phi scan of all the reflections of zinc oxide, and the rocking curve shows that the rocking curve full width half maxima is less than 1 degree. That means it is a very nicely grown film using PED method. And you would also see how PED is very critical to the processing gas. For example, this is a comparison made between PED and Pld. For 8 milliliter oxygen pressure in combination with hydrogen, you can see the resistivity of your tin oxide. it is fairly low, it is nearly metallic with the Pld, but for the same 8 millitorr with Pd you can see the resistance is of the order of 10 power 6. Therefore, the purging gas or the atmosphere that you use is very sensitive. So you need to have an optimum for Pd process, and similarly one can make very nicely grown film of gallia, which is also useful for optoelectronic applications. As you can see here, this is not exactly a single crystalline film, this is a polycrystalline film grown on sapphire substrates. And LaSr MnO3, in the last lecture I mentioned how manganite films can be nicely grown and they show the critical metal insulated transition. Same is the case, but again gives you an idea how the transition, metal insulated transition, can change with the gas that you use. In this case Pd in argon gas gives you a metal insulated transition which is shifted by nearly 50 Kelvin, whereas if you deposit this in gas in oxygen atmosphere, you get a room temperature metallic film. So we can make even manganite films with ease, and this is the deposition chamber that we have at IIT. This facility is there, and we can try to grow films of a variety on a variety of substrates. So this is the processing chamber, and this is the 6 target carousel that we have, and the whole thing is actually triggered using a computer. You can trigger the electron beam source, and this is one of the pictures taken at IIT Kanpur where you are ablating manganite films, and this is the typical plasma that is generated during the process. I will give you an example of how a polymer can be deposited. PTFE is a well known polymer which is called Teflon, and to ablate a material like that is impossible using Pld because of the optical absorption coefficient, which is quite different. As a result, it is not possible to ablate that easily using a Pld process, but you can see in Pd you can deposit such a film, and room temperature grown film shows the X-ray pattern which is typical of the target. And suppose you grow the same film at 100 degrees C, you see a amorphous state, and that is what you see from the TEM also. You have a crystalline film pattern emerging. How do I know? Because you are controlling in nano size, it is very difficult to know whether you deposited any film or not. If you are going to deposit on a Teflon coated glass, this is the Teflon coated glass, and this is on water droplets on glass, you can clearly see that the contact angle changes in the Teflon coated glass, meaning you have made a very effective coating of Teflon on the glass. So you can also see the IR very clearly showing that PTFE can be made using Pd, and in room temperature it gives a SEM feature like this, but when it is going to 100 degrees C, you can see a considerable loss in the fluorine content. Therefore, it is not really Teflon, but it is actually a non-stoichiometric polymer film, and this is the SEM of the target. You can see a very nicely cut solid surface of a polymer, and the microstructure changes when you try to deposit this film with different temperatures. And this is another example of how the crystallinity of the polymer varies from room temperature to 100 to 300 and to 500. Although the X-ray remains the same, it is very tempting to conclude that I am making PTFE film, but as you see here, you go down this SEM features, you can clearly see the microstructure changes, which means when you deposit or when you post anneal these films at higher temperature, you are actually losing quite amount of fluorine. So care should be taken to optimize the condition, and if you go to 500, actually the compound has transformed into mere carbon. So what you see here is nothing but carbon. So we need to understand this dynamics closely when you deposit PED, and it is also possible for us to gauge what is the thickness of this film that you are making, and using a profilometer it is possible to measure exactly the thickness of your PTFE layers. This is a typical AFM image of the film, and we can also do some nano structuring. You can write IIT Kanpur as a nanostructure, and length and width of each line is 1 micron and 44 nanometer respectively. So, you can actually do this sort of writings on polymer films. It is possible once you write using electron beam, you can try to cap this with any sort of dopants. So, you can actually try to fabricate any device by nanostructuring these polymeric surfaces. And this is another effort where you can use PED to make devices. I want to make a spintronic device, then I can actually go through this protocol. I first take a glass electrode like this 5 mm by 5 mm, and I can put a stripe. The first black stripe what you see here is nothing but iron stripe, and on the iron stripe I can actually put a PTFE square layer, and then on the top of the PTFE layer I can put another iron stripe. So, this is iron electrode and iron electrode, and PTFE is sandwiched between two iron electrodes. So, the AFM of each of this layer is shown on the top. You can see the microstructure is varying. The microstructure of the top electrode is quite different from bottom electrode, because you are heating this sample during deposition at 250 degrees C. Therefore, you get a fine grained structure compared to amorphous room temperature grown film. So, once you make this film, you can actually measure the resistance by applying voltage across these two ends, and you can measure you can apply current across this and measure the voltage across these two leads. So, this way you can make a plot of resistivity, and before that, if you take a look at the individual layers, you can see the bottom and the top layers do show different coercivity, and in a device they typically show this two-step loop, and this two-step loop is very critical or characteristic that a device is made, meaning the electrons are now tunneling through the polymeric layer, and only then you will see this sort of a two loop situation. But if you actually measure for that device with the polymer thickness varying from 3 nanometer to 4 nanometer, what you really see is pinholes which are short circuiting the top and the bottom electrode. As a result, you get a magnetoresistance which is negative in nature. If it is negative, that means there is a short circuiting between this electrode and this electrode via pinholes which are formed by PTFE. Therefore, this is not the desirable one. Therefore, what I can do is I can increase this layer thickness of PTFE which is in the middle, and if I increase it to say 6 nanometer, then immediately you see the magnetoresistance switches to positive in nature, which means the device is actually operating. So, this is a very useful information to understand how PED can be used for making critical devices. It is not just making films, you can make devices. And how do I know that I have made a device? If you actually do R versus T plot, typical values of your resistance has to be something like this, say 95 ohms. What does it mean? The iron electrodes are actually delinked, therefore resistance has gone up. If through the pinholes they are short circuited, the resistance will be less than a ohm, it will be in milliohm. That means both the electrodes are in contact with each other, therefore resistance will give you a useful map whether your device is really flat and it is working or not. So, PED can help us make films like this, and this is incidentally one of the good examples of a tunneling magnetoresistance curve. Lastly, I would like to show some example of yttrium barium copper, which is a superconductor, and how this can be deposited. And Christian group have reported how this can be made not just as a film but as a tape, because for practical applications you need to use it as a tape, and this is the profile where they have used it. As you can see, this is not just a substrate, but this is a polymer tape material called rabbits. So rabbit tapes are nickel tungsten tapes which can be rotated like a reel, and as the reel is being rotated you can try to deposit yttrium barium copper on the substrate, and therefore you can do a reel to reel deposition, which is one of the biggest advantage with Pd process. This cannot be done with ease with the Pld instrument. So that way you can actually make a substantially good application oriented depositions using Pd, and you can also map depending on the pulse time, deposition time, how the composition varies. This should be your actual composition 1:1.6:3 for yttrium barium copper, and as you are keeping on pulsing, you can stop at some counts and see what is the composition. As you would see, copper does not suffer in stoichiometry, but there is a give and take between yttrium and barium as you keep on progressively depositing high Tc films. So you need to have some idea how the chemical composition can vary, and also the distance between target and the substrate is determined. If you are going to keep it at 6 centimeter, you can see the Tc is varying as a function of millitorr of oxygen partial pressure. If you are going to keep it at 7, then you can see you can achieve a good stoichiometric film even below 50 millitorr. So all this are very sensitive and one depends on the other, therefore depending on the system we need to make a compromise, and these are some of the superconducting films. These are the actual plots of yttrium barium copper oxide. As you see, a typical superconductor will show a metallic behavior and then it drops down to 0, shows absolute resistivity at 90 K, and such films can be easily grown with PED technique. So in one sense we can sort of map to understand that for various compositions you need various mapping. If you are going to use alumina target, probably the distance or the target mount has to be like this. If you are going to use a copper plate, then you need to go for a probe like this. So different mounting approaches are also useful depending on the sort of material that we are using, and this also gives us some idea about the peak signal and the number of pulses. As you can see here, you can easily do it for copper, whereas when we go for alumina targets, the ion probe peak voltage is fairly low, and if you want to achieve 1 angstrom per pulse, then you need to sufficiently go for a compromise even on the target mounting approach. So all these are very important when we try to look at PED process. So to sum up, some word of comparison between PED and Pld. PED is having its own limitations in terms of the stringent parameters that are critically linked between each other. For example, target distance, the amount of or the millitorr of the gas that you are using, the nature of gas that you are using, and then the probe voltage, electron beam that is coming, and how the distance is kept between the target and the substrate. All these are very sensitive. In case of Pld, this is not too critical, though. The partial pressure of the oxygen or argon is very critical in Pld process. So with a fair amount of understanding, it is possible to extend Pd process to a variety of useful applications, and therefore more studies will be done, especially for device applications using Pd. So with this I stop.